Hi everyone, welcome back. In this lecture, we are going to understand how Java HashMap works internally. A HashMap stores data as key value pairs. The key identifies an entry and the value represents the data associated with that key. For example, suppose we store the key name with the value Ramesh. We can write this operation as put name Ramesh. Now the important question is this: how does HashMap decide where to store this entry? And when we call get using the same key, how does HashMap find the value quickly? Let's understand the complete process step by step. The first step is create a key value pair. In our example, name is the key and Ramesh is the value. Internally, HashMap stores this information as an entry containing the key, value, calculated hash, and a reference used when multiple entries share the same bucket. The key must be unique inside the map. If we add another value using the same key, HashMap updates the existing value instead of creating a duplicate key. The second step is get the hash code and spread the bits. HashMap first calls the hashcode method on the key. Suppose the hashcode of name is 35. HashMap does not simply use the raw hashcode without any processing. It performs an internal bit mixing operation. This operation mixes some higher bits into the lower bits and produces a better distributed hash value. This matters because the lower bits are used while selecting the bucket. Better hash distribution usually means fewer collisions. For this beginner-friendly example, assume the mixed hash value is also 35. The third step is calculate the bucket index. HashMap uses an internal array of buckets. Each bucket has an index starting from 0. Suppose the current capacity is 16. That means the bucket indexes are from 0 to 15. HashMap calculates the bucket index using this formula. Index equals n minus 1, bitwise and hash. Here, n represents the current capacity. In our example, n is 16 and the mixed hash is 35. So the calculation becomes 15, bitwise and 35. The result is 3. Therefore, the entry will be stored in bucket index 3. The fourth step is store the entry in the bucket array. HashMap goes to bucket 3. If the bucket is empty, it stores the new entry there. So bucket 3 now contains the key name and the value Ramesh. This is the normal case when no other entry is already using that bucket. But different keys can sometimes produce the same bucket index. This situation is called a hash collision. The fifth step is handle collision using a list or tree. Suppose another key called nickname with the value Ram also produces the mixed hash 35 and bucket index 3. Now both entries belong to the same bucket. HashMap stores these entries together inside that bucket. For a small number of entries, the bucket behaves like a linked list. The entry name and Ramesh may point to the next entry, nickname and Ram. A collision does not mean that one entry replaces another. The keys are different, so both entries can remain in the same bucket. If one bucket becomes heavily populated, HashMap may convert that bucket from a linked list into a red-black tree. In the open JDK implementation, treeification becomes possible when the bucket reaches the treeification threshold of 8 entries and the complete table capacity is at least 64. If the capacity is below 64, HashMap normally resizes the table instead. During resizing, if a tree bucket becomes small enough, around the untreeification threshold of 6, it may be converted back into a list. The tree structure improves lookup performance when many entries exist in one bucket. The sixth step is retrieve a value using the hash and equals method. Suppose we call getName. HashMap repeats the same main calculations. First, it calls hash code on name. Next, it spreads the hash bits. Then it calculates the bucket index using the current capacity. The result is again bucket 3. HashMap can now go directly to that bucket instead of checking every entry in the map. Inside the bucket, HashMap first compares the stored hash value. If the hash matches, it then compares the keys. It checks whether they are the same object or equal according to the equals method. When the key name matches the stored key name, HashMap returns Ramesh. This explains why both hash code and equals are important for HashMap keys. Equal keys must produce the same hash code. If a custom key class implements equals but does not implement hash code consistently, HashMap may fail to locate the expected entry correctly. It is also better to use immutable keys. Avoid changing fields that participate in equals or hash code after inserting the key. If those fields change, the key may produce a different hash and point to a different bucket during lookup. The seventh step is resize when needed. As more entries are inserted, the bucket array can become crowded. HashMap uses a load factor to decide when resizing should happen. The default load factor is 0.75. The resize threshold is calculated as capacity multiplied by load factor. For example, if the capacity is 4, the threshold is 3. When the number of entries grows beyond the threshold, HashMap creates a larger bucket array. The capacity usually doubles. So a capacity of 4 becomes 8. HashMap then redistributes the existing entries across the new bucket array. This redistribution helps reduce collisions and maintain efficient operations. Now let's understand the key design rules. The first rule is to implement equals and hash code consistently. If two keys are equal, they must return the same hash code. The second rule is to prefer immutable keys. Do not change the fields used by equals and hash code after inserting a key. The third rule is that keys are unique. Adding an existing key updates its value instead of adding another entry for the same key. Now let's review some important HashMap characteristics. HashMap allows one null key and multiple null values. It does not guarantee insertion order or any fixed iteration order. It is also not synchronized or thread safe by default. Now let's understand the performance. In the average case, operations such as put, get, remove and contains key are expected to take constant time, written as O of 1 when hashes are distributed properly. If one bucket becomes a long linked list because of many collisions, lookup inside that bucket may take O of n time. If the bucket has been converted into a red-black tree, lookup can improve to O of log n. So let's summarize the complete flow. First, HashMap receives a key value pair. Second, it calls hash code and spreads the hash bits. Third, it calculates the bucket index. Fourth, it stores the entry in that bucket. Fifth, it handles collisions using a linked list or a red-black tree. Sixth, during retrieval, it uses the hash and equals method to locate the correct entry. And seventh, when the number of entries crosses the threshold, HashMap resizes the bucket array and redistributes the entries. That is how Java HashMap stores and retrieves data internally. Thanks for watching, and I will see you in the next lecture.